6 detection methodologies and future research directions. 6.1 Current observational limitations. The investigation of 3I Atlas highlights significant limitations in our current capabilities for characterizing unusual astronomical objects. Our primary detection methods rely largely on passive observation of reflected sunlight and natural emissions, providing limited insight into the internal structure or potential artificiality of distant objects. The resolution of even the most advanced telescopes, including the James Webb Space Telescope and upcoming facilities like the Vera C. Rubin Observatory, remains insufficient to directly image surface features of 3I Atlas in detail, forcing reliance on indirect methods to infer its nature. These observational constraints fundamentally limit our ability to distinguish between natural and artificial explanations for the object's anomalies, creating ongoing uncertainty about its true nature. The challenges are further compounded by the rapid motion and transient nature of 3I Atlas's passage through our solar system. Unlike stationary astronomical objects that can be observed repeatedly over extended periods, 3I Atlas represents a fast-moving target with a limited observational window before it recedes into interstellar space. This temporal constraint has forced astronomers to prioritize certain types of observations over others, potentially missing crucial data that could resolve the object's mysteries. Additionally, the distribution of observational resources across multiple institutions and countries has complicated coordinated observation campaigns, with data sharing and analysis methodologies varying significantly between research groups. These limitations highlight the need for improved protocols and capabilities for responding to future interstellar visitors. 6.2 Recommended future observations and analyses. Despite the challenges, several observational approaches could potentially yield valuable insights into the nature of 3I Atlas in the limited time remaining. High-resolution spectroscopic monitoring across multiple wavelengths could help verify claims of anomalous metal concentrations and provide better understanding of the object's chemical composition. Simultaneous multi-observer campaigns could help resolve the rotational dynamics and potentially identify additional anomalies in light curves or outgassing patterns. Radar observations, though challenging given the object's distance and size, could provide unprecedented information about its internal structure and density distribution, potentially revealing evidence of artificial construction. Beyond immediate observations of 3I Atlas itself, the broader scientific community should consider developing dedicated capabilities for future encounters with unusual interstellar objects. This might include pre-approved rapid response protocols for major observatories, standardized data collection and sharing methodologies, and potentially even spacecraft missions designed for rapid interception of future interstellar visitors. The development of specialized analytical techniques focused on distinguishing natural from artificial objects would represent a valuable contribution to the field of astrobiology and CT research. Additionally, increased attention to the camouflage hypothesis might inspire new observational approaches designed to detect imperfections in natural mimicry, potentially identifying telltale signs of artificiality that would otherwise go unnoticed. 7. Conclusion. The comprehensive analysis of three IATLAs presented in this paper reveals a pattern of anomalies that collectively challenge natural explanation and warrant serious consideration of potential artificial origin. From its fixed geometric shadow and symmetrical jets to its anomalous, non-gravitational accelerations and peculiar chemical signatures, the object presents a constellation of peculiarities that distinguish it from both solar system comets and previous interstellar visitors. While each anomaly might be explained individually through ad hoc natural mechanisms, their convergence in a single object presents a statistical improbability that justifies expanded investigation and analysis of non-natural possibilities. The potential implications of 3I-ATLAS's artificiality are profound, touching upon fundamental questions about intelligence in the cosmos and humanity's place in the universe. Confirmation that we are not alone in the cosmos, or even that our solar system has previously hosted other technological civilizations, would represent a paradigm shift comparable to the Copernican or Darwinian revolutions in its impact on human self-understanding. Even if 3I Atlas ultimately proves to be a natural object, its unusual characteristics highlight significant gaps in our understanding of comet formation and evolution, particularly in interstellar environments. The scientific investigation of this enigmatic object therefore represents valuable research regardless of its ultimate origins, expanding our knowledge of the diversity of celestial bodies and potentially revealing new astrophysical processes. As 3I Atlas continues its journey through and eventually out of our solar system, it leaves behind a transformed scientific landscape in which the possibility of encountering extraterrestrial technology must be considered a legitimate aspect of astronomical research. The object serves as a powerful reminder that our current understanding of the cosmos remains provisional and subject to revision through new discoveries. Whether natural or artificial, 3I-ATLAS has already achieved something remarkable. It has challenged our assumptions, expanded our imagination, and reminded us that the universe likely holds wonders beyond our current comprehension. In this respect, the object represents not merely a scientific puzzle, but an invitation to cosmic humility and renewed curiosity about the strange and wonderful universe we inhabit. The detection of 3I Atlas in July 2025 marks a watershed moment in modern astronomy, representing only the third confirmed interstellar object observed traversing our following the enigmatic 1I Almuen of 2017 and the more familiar comet 2I Borisov in 2019. This latest visitor from distant stars has presented scientists with an unprecedented opportunity to study material unambiguously originating from beyond our solar system. Designated C2025N1, upon its discovery by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, the object immediately distinguished itself through a series of anomalous characteristics that have ignited scientific debate and public imagination alike. The significance of 3I-ATLAS extends far beyond its interstellar origins. As it journeyed toward perihelion on October 29, 2025, increasingly sophisticated observations from both ground-based telescopes and space observatories revealed a constellation of anomalies that collectively challenge conventional astrophysical models. From its unusual chemical composition to its puzzling physical behavior, 3.1 Atlas has prompted serious scientific discussion about the nature of interstellar objects and even the possibility that we might be observing something more extraordinary than a mere comet, a technological artifact from another civilization. This paper provides a comprehensive analysis of the 3I-TLAS phenomenon, examining both natural and artificial explanations for its most puzzling characteristics. We explore the object's discovery and orbital properties, its physical and chemical anomalies, the controversial nickel detection, and the broader implications for our understanding of intelligence in the cosmos, while maintaining scientific rigor and acknowledging the preference for natural explanations within the astronomical community. We seriously consider the evidence that might point toward an artificial origin for this mysterious interstellar visitor. The story of 3I-ATLAS began on July 1st, 2025, when the NASA-funded Atlas Survey telescope at the Rio Hurtado Observatory in Chile detected a faint object of apparent magnitude 18 moving through the border region between the constellations Serpens Cauda and Sagittarius. Initially designated a 11PL3Z, the object was immediately notable for its high inbound velocity of approximately 61 kilometers per second relative to the Sun, suggesting it might not be gravitationally bound to our solar system. At discovery, it was located 3.50 astronomical units from Earth and 4.51 astronomical units from the Sun, placing it already within the inner solar system at the time of identification. Within hours of its initial detection, astronomers worldwide began conducting follow-up observations. The critical question was whether this was merely another solar system comet or asteroid, or something far more interesting, our third confirmed interstellar visitor. The evidence quickly pointed toward the latter interpretation. Pre-discovery observations were soon identified, and data from the Zwicky transient facility dating back to the 14th of June 2025, and even earlier observations from the 7th of May 2025 were eventually recovered from NASA's TESS satellite data. These extended observational arcs allowed for precise orbital calculations that confirmed the object's interstellar status. On the 2nd of July 2025, just one day after its initial detection, the Minor Planet Center officially announced the discovery and designated the object 3I Atlas, acknowledging it as the third confirmed interstellar object. The MPC also assigned it the cometary designation C-2025N1 Atlas, reflecting early observations suggesting cometary activity. By this time, the MPC had collected 122 observations of 3I Atlas from 31 different observatories, providing a robust dataset for initial analysis. The orbital characteristics of 3I-ATLAS immediately distinguished it from both previous interstellar visitors and native solar system objects. With an orbital eccentricity of approximately 6.1, the object's hyperbolic trajectory firmly established its interstellar origins. This extreme eccentricity far exceeds the values observed for 1I Oumuamua, approximately equals 1.2, and 2I Borisov, 3.36, indicating that 3I Atlas may have originated from a different stellar environment or been subject to different ejection mechanisms. Analysis of 3I-ATLAS's trajectory suggests it likely originated from either the Milky waves-thin disk or thick disk population of stars. This provenance carries significant implications for the object's age and history. If it originated from the thick disk comprising older stars that formed early in the galaxies, HISTORY 3I Atlas could be at least 7 billion years old, potentially older than our solar system itself. This remarkable antiquity means the object could preserve information about planetary formation processes under conditions quite different from those that prevail in our own solar nebula. The object's orbital inclination of approximately 175 indicates a retrograde orbit relative to the plane of the solar system, a characteristic shared with 2I Borisov but distinct from the more moderate inclination of Oumuamua. Interestingly, 3I ATLAS's orbital plane is inclined only about 4.89 to the ecliptic, an alignment that some researchers have noted is statistically unusual, with a random probability of approximately 1 in 500. While this alignment could be coincidental, it has fueled speculation about possible intentional targeting of our solar system's planetary plane. 3.1 ATLAS made its closest approach to the Sun, perihelion, on the 29th of October 2025, at a distance of 1.36 astronomical units, approximately 203 million kilometers. This placement between the orbits of Earth and Mars provided favorable observational geometry for detailed study, while the object's minimum orbit intersection distance, MOID, with Earth of 0.36 astronomical units ensured it posed no impact threat. The object reached its maximum orbital speed of approximately 68.3 kilometers per second at perihelion, characteristic of hyperbolic trajectories. The observational campaign for 3I ATLAS benefited from its relatively early detection compared to previous interstellar objects. Unlike Oumuamua, which was discovered as it was already departing the inner solar system, 3.1 Atlas was identified well before perihelion, allowing astronomers to monitor the development of its activity over several months. This extended observational window proved crucial for documenting the evolution of its coma composition and detecting the unusual phenomena that would later fuel scientific debate. The approach of 3I Atlas toward solar conjunction in late October 2025 temporarily limited observational opportunities, but the post-conjunction period from November 2025 through January 2026 provided a final window for detailed characterization before the object receded into interstellar space. During this period, astronomers employed a comprehensive suite of observational tools, including spectroscopy, polarimetry, photometry, and direct imaging, to unravel the mysteries of this cosmic visitor. One of the most visually striking anomalies observed in 3I Atlas is the presence of a geometrically fixed shadow that maintains its orientation despite the object's rotation. Natural comets typically exhibit surface features and shadows that rotate with the nucleus, creating predictable variations in brightness and morphology. In contrast, high-resolution images of 3I Atlas from the Hubble Space Telescope and other observatories revealed a persistent linear dark lane cutting across the coma that appeared unaffected by the object's 16.2-hour rotation period. This fixed shadow phenomenon represents a significant challenge to conventional cometary science. In natural comets, such stability would require an unprecedented alignment of rotational axis with jet direction or some form of internal structure that maintains surface features in a fixed orientation relative to external references. The remarkable stability of this feature across multiple rotation cycles suggests either extraordinary natural circumstances or potentially something more engineered, perhaps a structural element or thermal regulation system that maintains its orientation through internal stabilization mechanisms. The fixed shadow has been observed consistently across different instrumentation and by multiple independent observers, ruling out instrumental artifacts as the sole explanation. Its geometric precision, described by some observers as ruler straight, further distinguishes it from the typically irregular shadows cast by natural topographic features on comet nuclei. While not conclusive evidence of artificiality, this anomaly represents one of several peculiar characteristics that collectively demand explanation. Another notable anomaly of 3I-ATLAS is the presence of unusually symmetrical jet structures that maintain their configuration despite the object's rotation. Natural comets typically exhibit asymmetric, variable jets that shift and evolve with rotational phase, solar heating variations, and surface erosion. In contrast, 3I-ATLAS displays crisp, linear emission spikes that appear mirrored across the nucleus and maintain their orientation across multiple observation cycles. These symmetrical jets behave unlike any observed in solar system comets. As the comet rotates with its 16.2-hour period, the jets should theoretically smear into spiral patterns due to the changing orientation of the nucleus. Instead, they remain persistently aligned, suggesting some form of compensation for rotation. Natural explanations for this phenomenon would require exceptionally fine-tuned geometry, such as vents located precisely at the rotational poles, with perfect alignment to the rotation axis. The probability of such alignment occurring naturally is statistically low, though not impossible. The stability of these jet structures becomes particularly intriguing when considered alongside the non-gravitational acceleration measurements discussed in Section 3.3. If the jets represent the source of this acceleration, their fixed orientation would explain the consistent direction of the non-gravitational force. However, maintaining such alignment naturally in a rotating body would require extraordinary circumstances, potentially pointing toward more engineered solutions such as gimbaled nozzles or internal flow directing mechanisms that compensate for rotation. Careful tracking of 3I-ATLAS's position has revealed subtle but significant non-gravitational acceleration that cannot be explained solely by gravitational forces. Measurements indicate a small but persistent acceleration of approximately 0.02 millimeters s², which remains remarkably constant in both magnitude and direction. This acceleration aligns with the object's orbital plane rather than following the typical pattern for comets, where non-gravitational forces usually point away from the Sun due to solar heating effects. The nature and magnitude of this non-gravitational acceleration have become a central point in the debate about the object's origins. In natural comets, such accelerations are typically attributed to asymmetric outgassing, which produces a rocket-like effect as gases are ejected preferentially from certain regions of the nucleus. However, the consistent direction and magnitude of 3I-ATLAS's acceleration, LARGEL, while unaffected by its rotation or changing solar distance, present challenges to this conventional explanation. The acceleration pattern observed in 3I-ATLAS bears intriguing similarities to that of low-thrust propulsion systems used in human spacecraft, such as ion engines or continuous propulsion methods. While the acceleration is minuscule compared to conventional rockets, it is precisely the magnitude that would be expected from a long-duration interstellar probe using efficient, low-thrust propulsion. This similarity has led some researchers to speculate that we might be observing a form of controlled thrust rather than natural outgassing. Spectroscopic observations of 3I-ATLAS have revealed several compositional peculiarities that distinguish it from typical solar system comets. Observations from the James Webb Space Telescope indicate that the coma of 3I Atlas exhibits an unusually high carbon dioxide to water ratio of approximately 8:1, among the highest ever measured in any comet. This ratio stands in stark contrast to most solar system comets, which typically show much higher water content relative to carbon dioxide. Additionally, spectroscopic monitoring has revealed an unusual depletion in carbon chain molecules, particularly a low C/Cn ratio, which typically indicates substantial thermal processing that would be unexpected in a pristine interstellar object. These chemical anomalies collectively suggest either formation in an extremely cold environment with different chemical fractionation processes, or potentially more exotic origins that might include artificial construction. The chemical composition of 3I-ATLAS becomes particularly intriguing when examined in the context of potential artificiality. The high CO ratio could potentially serve functional purposes beyond camouflage, perhaps as a propellant reserve for a propulsion system utilizing naturally available materials. Similarly, the unusual carbon chain depletion might indicate the use of processed materials or the operation of internal systems that selectively release certain volatiles while retaining others. Perhaps the most controversial observations regarding 3I Atlas involve claims of anomalous nickel vapor detection in its coma. Beginning in July 2025, observations using the Very Large Telescope's X-Shooter and UVES spectrographs detected spectral lines consistent with atomic nickel vapor at distances of approximately 3.88 astronomical units from the Sun. This detection was itself unusual, as metals like nickel typically vaporize at much higher temperatures found closer to the Sun. The nickel detection became increasingly extraordinary as monitoring continued. Between July and August 2025, the production rate of nickel atoms increased approximately 25-fold, reaching an estimated 47 billion nickel atoms per second. This rapid increase in metal production far exceeded typical patterns observed in natural comets and suggested an activation or warming process unlike anything previously documented. Most puzzling of all was the absence of detectable iron in the spectra. In virtually all natural space objects, nickel and iron appear together in predictable ratios, reflecting their cosmic abundance, typically around 1/16 by mass. The complete absence of iron spectral lines in 3I-ATLAS, despite strong nickel emissions, represents a departure from all known natural space chemistry. This nickel without iron signature has been described as scientifically revolutionary and has prompted serious consideration of alternative explanations, including possible artificial origins. The scientific community has proposed several potential explanations for the unprecedented nickel detection in 3I Atlas. Natural hypotheses suggest the presence of exotic nickel-bearing compounds that could release nickel atoms at lower temperatures than pure metal. Specifically, researchers have proposed that nickel carbonyl compounds containing nickel bound to carbon monoxide or other metal organic complexes might be present in the comet. Such compounds could theoretically decompose under solar radiation, releasing nickel atoms while keeping iron locked in more stable compounds. An alternative natural explanation involves cosmic ray processing of surface materials over millions of years. Galactic cosmic rays, high-energy particles, traveling through space could potentially alter surface chemistry in ways that separate nickel from iron or create nickel-enriched surface layers. If 3I-ATLAS indeed originated from the galactic thick disk and is 7 billion years old or more, it would have had ample time for such processing to occur. The more speculative artificial hypothesis suggests that the nickel signature might reflect manufactured components within the object. On Earth, industrial processes routinely separate nickel from iron to create specialized alloys with particular properties like radiation resistance or thermal stability. If 3I-ATLAS represents a technological artifact, its nickel emissions might result from the vaporization of such manufactured materials as the object approaches the Sun. This would explain both the absence of iron and the unusual scaling of nickel production with decreasing solar distance. The possibility that 3I Atlas might represent a technological artifact rather than a natural object has been seriously proposed by several researchers, most notably Harvard astronomer Avi Loeb, who previously suggested similar possibilities for Oumuamua. Loeb currently estimates a 30 to 40% probability that 3I Atlas does not have a fully natural origin, based on what he identifies as 7 distinct anomalies in its behavior and character. Proponents of the artificial origin hypothesis point to the convergence of multiple anomalies as suggestive evidence. While each peculiarity might be explained individually through natural mechanisms, the combination of fixed geometric features, symmetrical jets, consistent non-gravitational acceleration, unusual chemical ratios, and the unprecedented nickel signature collectively presents a pattern that some researchers argue is more consistent with engineering than natural processes. The statistical probability of all these rare characteristics occurring together in a single natural object appears low, though not impossible. The artificial hypothesis specifically suggests that 3I Atlas could be an autonomous interstellar probe designed to mimic a natural comet for camouflage purposes. Such a probe might employ controlled outgassing of stored volatiles both for propulsion and to maintain its natural appearance. The fixed shadow could represent a structural element imperfectly concealed beneath a natural-looking crust, while the symmetrical jets might indicate engineered nozzle systems designed to provide directional thrust while maintaining the comet-like illusion. If 3I-ATLAS indeed represents an artificial construct, several potential mission profiles could explain its presence in our solar system. The most conservative scenario involves a reconnaissance or scientific survey mission, potentially originating from a civilization seeking to study our planetary system with minimal disturbance to its natural development. Such a mission profile would explain the employment of sophisticated camouflage, as the observing civilization might wish to avoid alerting potential inhabitants to their presence. Alternative mission profiles might include a message-bearing capsule intended to preserve knowledge across interstellar distances or geological timescales, similar in concept to human projects like the Voyager Golden Records, but with significantly more advanced implementation. In such a scenario, the cometary disguise might serve to protect the object from interference until the recipient civilization reaches a sufficient technological level to detect its artificial nature. A more unsettling possibility positions 3I Atlas as one node in a distributed monitoring network maintaining surveillance over our solar system across immense timescales. This would be consistent with the lurker or sentinel hypothesis discussed in SETI circles, wherein advanced civilizations deploy long-duration autonomous monitoring systems to track developments in promising planetary systems. The apparent activation of 3I-ATLAS's outgassing as it entered the inner solar system could potentially represent the awakening of such a sentinel in response to human technological activity. The potential artificiality of 3I-ATLAS raises fascinating questions about the engineering approaches that might be employed by an advanced spacefaring civilization. The object's apparent ability to maintain fixed external features despite rotation suggests sophisticated internal stabilization systems, potentially employing technologies similar to control moment gyroscopes used in human spacecraft. Similarly, the consistent non-gravitational acceleration could be produced by advanced propulsion systems operating on principles similar to human ion thrusters, but with far greater efficiency and longevity. The extended operational lifetime required for an interstellar probe presents significant engineering challenges. If 3I-ATLAS originated from the galactic thick disk and is indeed over 7 billion years old, it would represent technologies capable of functioning across cosmological timescales. Such longevity might be achieved through redundant systems, self-repair capabilities, or extremely conservative design principles prioritizing durability over performance. From a power generation perspective, an interstellar probe would likely employ long-lived energy sources such as radioisotope thermoelectric generators, RTGs, similar to those used in human deep space missions, or potentially more advanced systems like fission reactors or even quantum power sources. The presence of such systems could potentially explain unusual thermal properties or minor elemental anomalies, though no direct evidence for such systems has been detected in observations to date. The mainstream scientific community largely favors natural explanations for the anomalies observed in 3I-ATLAS. NASA's lead scientist for solar system small bodies, Tom Statler, has stated unequivocally, "It looks like a comet." It does comet things. It very, very strongly resembles, in just about every way, the comets that we know. This perspective represents the consensus view among planetary scientists who acknowledge the object's peculiarities but consider them within the bounds of natural variation. The unusual chemical composition of 3I-ATLAS, including its high carbon dioxide ratio and potential nickel emissions, can be explained through exotic formation conditions in its home stellar system. Planetary systems forming under different conditions from our own, particularly around stars with different elemental abundances, might produce comets with distinctly different chemical signatures. As 3I-ATLAS potentially originated from an older stellar population in the galactic thick disk, its composition might reflect earlier galactic chemical evolution. The fixed geometric features and stable jets could potentially result from unusual nucleus geometry or internal structure. A comet with a highly elongated shape or particular mass distribution might maintain relatively stable orientation despite rotation. Similarly, internal plumbing systems that channel gas from depth to specific surface vents could potentially produce stable jet structures even as the nucleus rotates. While such configurations would be unusual, they remain within the realm of natural possibility. Critics of the artificial origin hypothesis frequently employ statistical arguments against the likelihood of humanity encountering an alien probe. Given the vastness of space and the relatively recent emergence of human technology, the probability of such an encounter appears low based on conventional SETI assumptions. However, proponents counter that if advanced civilizations are common and engage in extensive interstellar exploration, the discovery of such artifacts might be more likely than generally assumed. Another significant counter-argument involves anthropic reasoning and observation selection effects. As the third interstellar object detected in just 8 years, 3I-ATLAS suggests that such visitors may be far more common than previously believed. If the interstellar object population is indeed rich and diverse, we should expect to encounter unusual examples that challenge our expectations, based solely on solar system. In this view, 3I-ATLAS may be unusual but still natural and outlier in the statistical distribution of interstellar objects. The confirmation bias inherent in the search for extraterrestrial intelligence represents another important consideration. Humans may be predisposed to perceive patterns suggesting intelligence even in natural phenomena, a tendency that requires careful scientific discipline to overcome. Most scientists argue that extraordinary claims like the artificial origin of 3I-ATLAS require correspondingly extraordinary evidence, which they believe has not yet been provided. SETI scientist A.K.M. Isenal Hack has directly addressed claims that 3I-ATLAS might be an alien spacecraft in a paper responding specifically to Loeb's assertions. Hack argues that the object's retrograde orbital alignment with the ecliptic, while statistically rare with approximately 0.2% probability, is not impossible for natural interstellar objects. He notes that the galactic disk, which is where most stars are, is nearly in line with the solar system's ecliptic plane, making such alignments plausible for naturally ejected objects. Regarding the non-gravitational acceleration, Hack points out that while 2I Borisov exhibited slight non-gravitational acceleration attributed to outgassing, analysis of 3I-ATLAS has shown no evidence of acceleration beyond what gravity would cause in its light curve. This distinction from Alma Ma, which displayed clear non-gravitational acceleration, undermines arguments for artificial propulsion in the case of 3I Atlas. Hack also compares 3I Atlas's spectral slope with D-type asteroids and interstellar comet 2I Borisov, finding consistency with these natural objects. Based on its trajectory, spectra, and comet-like properties, he suggests that 3I Atlas could be a lithified clastic fragment from an exoplanetary sedimentary basin, an unusual but entirely natural object. The controversial nickel detection in 3I Atlas highlights the urgent need for verification through independent observation. The initial reports, while intriguing, require confirmation through more sensitive spectroscopic observations across a broader wavelength range. Future observations with the James Webb Space Telescope could potentially detect infrared signatures that ground-based telescopes cannot resolve, potentially identifying iron emission lines at different wavelengths or directly detecting proposed nickel carbonyl. The time evolution of the nickel signature as 3I Atlas recedes from the Sun may provide crucial diagnostic information. If the nickel emission decreases symmetrically with increasing solar distance, it would support natural heating processes as the explanation. Conversely, unusual temporal patterns in the nickel production rate might suggest more complex processes, potentially consistent with artificial systems responding to changing environmental conditions. Laboratory experiments simulating the proposed nickel carbonyl hypothesis could help assess its viability as an explanation for the observations. By recreating conditions similar to those in 3I Atlas's coma and monitoring the spectral signatures of various nickel compounds, researchers could determine whether the observed emissions can indeed be reproduced through natural chemistry or whether they truly represent an unprecedented phenomenon. The mysteries surrounding 3I Atlas underscore the importance of developing more sophisticated characterization techniques for future interstellar visitors. Polarimetric observations have revealed that 3I Atlas exhibits an unusually high degree of negative polarization at small phase angles, suggesting its coma contains dust particles with unusual properties. Further analysis of this polarization signature may provide insights into the size, shape, and composition of the dust particles, potentially distinguishing between natural and artificial explanations. Radar observations, though challenging given the object's distance and relatively small size, could provide unprecedented information about its internal structure. If conducted with sufficient resolution, radar imaging might reveal internal density, variations, or structural elements that could distinguish between a homogeneous natural nucleus and something with potentially engineered internal architecture. The development of real-time spectral monitoring systems, specifically designed for unusual astronomical targets, could capture the rapid color shifts reported by some observers of 3I Atlas. By documenting the spectral evolution of the coma across timescales from minutes to days, astronomers could determine whether these variations follow natural patterns of cometary activity or exhibit anomalies potentially suggestive of modulated emissions. The scientific discourse surrounding 3I Atlas has demonstrated the need for protocols for studying anomalous space objects. The controversy over data transparency and delayed release of observations highlights the importance of establishing clear guidelines for rapid data sharing when unusual objects are detected. Such protocols would ensure that the global scientific community can collaborate effectively to characterize transient interstellar visitors before they depart the inner solar system. The detection and analysis of 3I Atlas may motivate planning for dedicated interstellar intercept missions. The European Space Agency's Comet Interceptor project, scheduled for launch in 2029, represents a step in this direction, though current mission designs remain focused on solar system comets rather than the high-velocity trajectories characteristic of interstellar objects. Future mission concepts specifically designed for interstellar object rendezvous could provide definitive answers to questions about their nature and origin. The 3I Atlas phenomenon has also revealed gaps in our theoretical frameworks for understanding exotic chemistry and space environments. The potential detection of nickel vapor through mechanisms that operate at low temperatures suggests that our current models of cometary chemistry may be incomplete. Developing more comprehensive models that account for unusual molecular carriers and low-temperature reaction pathways would enhance our ability to interpret observations of future interstellar visitors. The arrival of 3I Atlas in our solar system represents a watershed moment in astronomical science, offering both unprecedented opportunities for interstellar material studies and profound challenges to our understanding of small-body astrophysics. This mysterious object has presented researchers with a constellation of anomalies, from its unusual mass and acceleration characteristics to its peculiar compositional signatures and bafflingly stable structural features that collectively resist straightforward explanation within existing paradigms. While the natural origin hypothesis remains the most scientifically parsimonious explanation, 31ATLAS has clearly exposed gaps in our knowledge of how planetary systems form and evolve across the galaxy, and what kinds of materials they eject into interstellar space. The object's characteristics suggest that planetary systems around other stars may produce small bodies with properties and behaviors not represented in our own solar system, potentially expanding our understanding of planetary science beyond the parochial perspective limited to our immediate cosmic neighborhood. The more speculative technological interpretations, while capturing public imagination and stimulating valuable discussion about how we might recognize extraterrestrial intelligence, currently lack empirical support and are considered unlikely by most experts in the field. Nevertheless, the serious scientific attention given to these possibilities reflects the truly extraordinary nature of 31ATLAS's observed properties and the recognition that our current models cannot fully account for all its features. As 3I Atlas continues its journey through and eventually out of our solar system, it leaves behind a transformed scientific landscape. The detection of this third interstellar visitor, with properties distinct from both previous objects, suggests that the galactic population of such wanderers may be far more diverse than previously imagined. Future discoveries enabled by advanced observatories like the Vera C. Rubin Observatory will likely reveal many more interstellar objects, potentially placing 3I Atlas within a spectrum of similar bodies or confirming its status as a genuine outlier. Regardless of its ultimate explanation, 3.1 ATLAS has already achieved something remarkable. It has reminded us that our galaxy still holds mysteries that challenge the limits of our current understanding, pushing scientific inquiry toward new questions and potentially toward revolutionary discoveries about the universe we inhabit. In this respect, whether 3I ATLAS proves to be an unusual natural object or something even more extraordinary, its passage through our solar system has permanently expanded the boundaries of astronomical science. The arrival of the third confirmed interstellar object, 3I ATLAS, presents not merely an astronomical curiosity, but a profound engineering and scientific puzzle. Its behavior deviates so significantly from established models of cometary science that it has prompted the documentation of at least 12 distinct anomalies, ranging from its non-gravitational acceleration to its unusual chemical composition. In any terrestrial engineering context, such a cascade of deviations would trigger a formal anomaly investigation and resolution (AI&R) process, a systematic methodology for identifying, analyzing, and resolving unexpected behaviors in complex systems. This paper applies such a disciplined, multidisciplinary framework to 3I Atlas, treating the solar system as a testing ground and the object as an unlabeled, potentially functional artifact. We will explore the hypothesis that convergent data from isotope geochemistry, ultra-high-resolution imaging, and autonomous systems engineering may provide the necessary criteria to distinguish a natural celestial body from a product of intelligent design. 2. The isotopic Rosetta Stone, decoding origins and engineering. The precise measurement of isotopic ratios is a cornerstone of modern cosmochemistry, serving as a reliable and long-lasting process tracer for understanding the origin and history of materials. For 3I ATLAS, isotopic analysis is not just a tool for dating, but the most potent available method for testing its provenance and potential artificiality. This equation highlights a critical challenge: to achieve the requisite precision on a potentially tiny sample from a fleeting target. Every aspect of the analytical process, from ionization efficiency to amplifier noise, must be optimized. Techniques like isotope ratio mass spectrometry, IRMS, which can maintain high precision over extended periods through careful calibration with laboratory working reference materials, would be crucial for this task. Given the limitations of remote spectroscopy, a sample return mission is the definitive approach for isotopic analysis. The primary scientific goal would be to search for isotopic anomalies that defy natural explanations. We would be looking for non-mass-dependent fractionation. Natural processes fractionate isotopes roughly in proportion to their mass difference. Industrial processes like uranium enrichment can create fractionation patterns independent of mass, a potential signature of engineering. Extreme enrichment or depletion. The intentional selection of specific isotopes for functional purposes could result in ratios that are outliers by many orders of magnitude compared to natural solar system values. For instance, water enriched in deuterium could be used for neutron moderation in a compact power source, while carbon-13 enriched CO might have specific thermal or structural properties. Unnatural elemental pairings. The reported high nickel content without corresponding iron is highly anomalous. In a natural body, nickel and iron are cosmically correlated. Their separation is a hallmark of metallurgical processing on Earth. The presence of other isolated, refined metals would be a powerful indicator of artificiality. 2.3 Cosmic ray chemistry versus engineered reservoirs. A natural hypothesis for the object's complex chemistry is cosmic ray processing. Over millions of years, high-energy particles can drive chemistry in ices, synthesizing complex organic molecules and altering isotopic ratios. However, the specific pattern observed in 3I ATLAS, the low carbon chain abundance, the specific cyanide and CO emissions suggest a selective chemistry, as if certain pathways are favored and others suppressed. An alternative engineered explanation involves internal isotopically tailored reservoirs. Imagine a probe with separate tanks holding different volatiles, each optimized for a function. Propulsion reservoir. Methane with a specific C1-C13 ratio for predictable thrust characteristics. Thermal management reservoir. CO enriched in C13 for optimized radiative or phase change properties. Shielding reservoir. Water with elevated deuterium content for effective radiation shielding. The coma we observe would be a blended release from these reservoirs, creating a composite isotopic signature that appears unnatural and selective when compared to the well-mixed, homogeneous composition of a primordial comet. The human eye, and indeed any single telescope, is fundamentally limited by the diffraction limit, which dictates the smallest resolvable detail. For a 1-meter telescope observing 3I Atlas at its closest approach, the nucleus would remain an unresolved point of light. To discern structure, we must turn to interferometry. As you correctly noted, interferometry combines light from multiple telescopes separated by a baseline, B, to simulate a single telescope with a diameter equal to that baseline. The achieved angular resolution, theta, is given by theta, approximately equals lambda b, where lambda is the wavelength of observation. The Event Horizon Telescope, EHT, with its Earth-sized baseline, achieved a resolution of 20 microsecunds, sufficient to image the shadow of a black hole in the galaxy M87. Applying a similar, albeit technologically daunting, optical interferometer to 3I Atlas could resolve features on the scale of tens of meters. With such resolution, we would move from speculation to direct observation. We would search for signature engineering, structural motifs that betray design. In a natural comet nucleus, we would expect an irregular potato-like shape, heavily cratered and fractured, with jets emerging chaotically from sun-warmed, volatile-rich patches. The structure would be that of a rubble pile, shaped by random collisions and aggregation. In an engineered object, we would look for geometric symmetry and patterns, not necessarily perfect symmetry, which would be obvious, but subtle alignments, repeating patterns of vents, or a consistent surface texture. Fixed structural elements. The dark lane that doesn't wobble could be directly imaged. Is it a long, straight crevasse? Or does it have the sharp geometric edges of a panel, a radiator, or a structural spar? evidence of layering, a sharp discontinuity between an outer, perhaps camouflaging, shell of natural-looking material and a denser, more structured inner core. Jet dynamics. Time-resolved interferometry could show if the symmetrical jets emanate from fixed points in space, requiring internal gimbaling or a network of fixed nozzles, rather than simply from the rotating surface. The technological challenges long integration, times on a faint, moving target, and the need for sophisticated adaptive optics and image reconstruction algorithms are immense. However, the principle is sound and lies within the foreseeable extension of current technology, such as that being advanced by the Very Large Telescope Interferometer, VLTI. Point 4. The longevity hypothesis, autonomous and self-repairing systems. If 3I Atlas were an interstellar probe, its most incredible feature might not be its origin, but its longevity. Surviving for millions of years in the harsh environment of interstellar space is an engineering challenge of the highest order. Intriguingly, our own engineering concepts are beginning to converge on solutions to this very problem. 4.1. The Modular, Autonomous, Reconfigurable Spacecraft, Mars. As you referenced, research teams are actively developing prototypes for modular spacecraft. These systems are composed of multiple intelligent modules that can detach, move, and reconnect autonomously. This architecture provides a pathway to longevity through several key features. Graceful degradation. If one module is damaged by a micrometeoroid impact or radiation, it can be isolated and its functions can be migrated to health. The system can route around damage much like the internet. Adaptive reconfiguration. The modules can rearrange themselves to optimize for changing conditions, shifting the center of mass for attitude control, reorienting solar panels, or reallocating power. Long-term maintenance. Over eons, a Mars-like probe could potentially cannibalize non-essential modules for parts to repair critical systems, allowing it to remain functional long after a monolithic probe would have failed. Rated for its observed anomalies. It would not be a pristine, perfectly functioning machine, but a degraded, ancient system running on backup systems and patchwork solutions. The stable but slightly erratic jets and thrust could be the result of a compromised but still semi-functional propulsion system, its control algorithms adapting to the loss of specific valves or sensors. The unusual chemical signatures could reflect the depletion of primary volatile reservoirs and a shift to using secondary, chemically different reserves. The fixed shadow could be a structural element of the internal modular frame, now partially exposed due to the loss of its camouflaging outer layer over millions of years. This hypothesis transforms 3I Atlas from a perfectly disguised probe into a venerable, limping mariner, a machine that has been running for so long that its original mission may be lost to corrupted memory, but its core programming to survive, navigate, and observe continues to execute. 5. The Pattern Recognition Engine, AI-driven anomaly detection. The human brain is excellent at pattern recognition, but is also constrained by cognitive biases. We often find what we expect to see. The data stream from 3I Atlas comprising light curves, spectra, polarimetry, and, potentially, interferometric data is vast and complex, containing subtle signals that may be dismissed as noise. 5.1. moving beyond human-limited analysis. As demonstrated in exoplanet studies, machine learning algorithms can detect subtle, repeating patterns in spectral data that human analysts overlook. Applying a similar AI-driven anomaly detection system to 3I Atlas would be a critical step in the process would be training. An AI model would be trained on a vast dataset of spectroscopic and photometric observations from known, well-understood solar system comets and asteroids. This establishes a robust baseline of normal behavior. Analysis. The model would then be fed all available data for 3I Atlas. Anomaly flagging. The AI would not be told what to look for. Instead, it would be tasked with identifying any and all statistical deviations from the trained baseline. It might identify subtle periodicities, complex cycles and emission lines that do not perfectly correlate with the 16.2-hour rotation, hinting at internal cycles or modulated processes. Unexpected correlations, a non-intuitive link between the intensity of a nickel spectral line and a specific phase of its orbit, suggesting controlled release. Structural patterns in noise, low-level signals that when stacked and analyzed reveal a non-random, information-rich structure. This approach is objective and exhaustive. The AI doesn't presuppose that comets must be natural. It simply reports, this one is different in the following specific, quantifiable ways. The patterns it finds could be the final, conclusive evidence of engineering a technosignature, not of. We equip ourselves with the tools needed to answer one of humanity's oldest questions. Whether 3I Atlas is a natural oddity or an artificial construct, its true value lies in pushing our scientific methodologies to their limits and beyond. It forces us to consider that the universe may not only be stranger than we imagine, but stranger than we can imagine, until we learn to look with new eyes and new tools. The messenger is here. It is now our task to decipher its language.